Hello, my dear friends. In this discussion, we're going to be looking at a solution to one-dimension wave equation, which is in form of a partial differential equation. So, first of all, before we go right away into this solution, I want to remind you about the applications of a wave equation. We have one of the applications being in medical and imaging. In medical and imaging, we use this 1D equation to study the propagation of sound waves through tissues, and this is very helpful during doing ultrasound. So, also in mechanical vibrations and structural engineering, we study this wave equation because it helps us to understand that the vibrations designing maybe shock absorption system in mechanical systems or in vehicles. We also find in structural engineering designing when you're designing the bridge. Obviously, it has some kind of deflections, it has some kind of vibrations, and so you need to determine the extent to which these vibrations are going to be transmitted via different components of the bridge. It's a number of things, a number of areas where you have the one-dimensional wave equation. Even in building sways, you'll find that you need to have a knowledge of this one-dimension equation. We also study this one-dimension equation because it helps us to analyze seismology and earthquakes. This helps us to model seismic waves as they travel through the earth during an earthquake event. So that is a small background on the reasons as to why someone at an advanced level needs to understand or study the one-dimension equation. So let's right away go to the problem that has been given to us. So the guiding question says a stretched string of length 50 centimeters is set to oscillate by displacing its midpoint by 2 centimeters from its rest position, and then releasing it obviously with zero velocity. So we are told that we are solve the one-dimensional wave equation. There 2u, which we said we can always use this other notation, ux is equal to 1 out of c squared utt. And so where c squared is equal to 1, that's what has been given to us for simplicity. And then we are told to determine the resulting motion ux of t. This is a x as a function, this is u, a function of x and t, but majorly this u is going to be describing the motion of the wave through this string. And x represents the position of this wave or the particle on the string vis-a-vis time, or at any particular instant you're going to have the position of any particle on the string moved, and then of course with respect to time. So we are told that this is what it is. First of all, in the beginning it was stretched and from 0 to 50. So then we held in the middle, at the midpoint of this string, then we stretched it by 2. So upwards here, we stretched it by 2. So the apex here is 2. And then we released it, of course, to have the motion. So for us to solve this problem, we are going to begin with, number 1, the boundary conditions. So the boundary conditions here are going to be, first of all, we have a u of 0, t equivalent to 0. Then we have u of 1 of actually 50, and t is equal to 0 also. And this is true because we have the endpoints. endpoints of the string are fixed. So if you have the endpoints of the string being fixed, you'll find that you'll have no motion of any particle at this end, at the beginning, and also no motion of any particle on the string at the end here at a distance equivalent 50 centimeters. So let's proceed. We also know that we have initial conditions. So this was boundary conditions, and we have initial conditions. So the initial conditions are from ux of 0, that is at t is equal to 0. We find that we are going to have a function f of x. But let's look at between 0 and 25. So between 0 and 25, 0 and 25 centimeters, you'll find that this is going to be a straight line. So if it becomes a straight line, we are going to recall y is equal to mx plus c. So if it is y is equal to mx plus c, what is m? M is the gradient of this line, and this is going to be 25. Remember, you are going to be having points like 0, 0, and then you have 25 and 2. So I'll have change in y over change in x. Just for purposes of understanding, I'll have 2 minus 0 divided by 25 minus 0, and this gives us 2 out of 25. So this means that our function f of x, which is y, is going to be, so our f of x is going to be 2 out of 25x, then plus c. So we can put in some values. We know that at 0, 0, okay, y is going to be 0, so we shall say 0 is going to equal to 20. This is going to be 2 times 0 divided by 25 plus c, and this gives us our c, the y-intercept being 0. So that means f of x is going to be 2 out of 25 x, that is between 0 less x less 25. So that is in between here and that. So you can see that is a straight line with a positive gradient. So what about between 25 and 50? You see that the line is falling, and we can use here, we can use either similarity of triangles, or we still use the equation of a straight line. So between 25 and 50 centimeters, you'll find that you have 2 points. You have 0 and 4, and then you have what? You have another point, which is 25 and 2. You have 25 and 2. But now, what if this 4 was not given? Because originally it wasn't given, I put it here. So what I do, I get what? I use similarity of triangles by saying this triangle here is similar to this bigger one, so that I will have 2. I'll have 2 out of 4. Okay, I'll have 2 out of x. For example, I'll have 2 out of x, and then what will happen? What will happen? I'll have 2 out of x equivalent to, which other line can we take? We'll take 0 to 25. So 0 to 25, and from here to here, 25. So I'll take 25 out of 50, 25 out of 50. So what will this give us? This means that our x is going to be 2 times 50 divided by 25. Obviously, this gives us 4. So that's where the 4 is coming from. So if that is the case, can we look for the gradient of the line there? So that gradient is going to be 2 minus, this is actually going to be what? This is going to be 2 minus 4. So 2 minus 4 divided by 25 minus 0. And this is giving us what? Negative 2 out of 25. So what about when we put it back, so of course f of x is going to be y is going to equal to negative 2 out of 25 x plus c. So how do we get c? We are going to use points. So put points of, we are going to use which one? We can take, we can either take 0 and 4, 0 and 4. Okay, we can take 0 and 4, so we can use 0 and 4, so that when we substitute in here, we'll have 4 is equal to negative 2 times 0 divided by 25 plus c, and then c is equal to 4. So meaning our f of x is going to be negative 2 out of 25 of x plus 4. So what does that mean? This means that negative 2x plus 100 out of 25, that is going to be the function f of x. So finally, this is going to be f of x equivalent to 100 minus 2x out of 25, and this is for x lying between 25 and 50. So that is x lying between 25 and 50. So we have already obtained now the 2 points, that is the boundary conditions and the initial conditions. So the first initial condition, we have 2x out of 25 between 0 and 25, and between 25 and 50, we have 100 minus 2x divided by 25. So let's proceed and see what happens. Then after there, we have another point whereby del u, del t. Remember, we are told that del u, del t, obviously this would give us, remember, del u itself is representing a position. Then if we divide it by a t, then we are talking about velocity. So at t is equal to 0, initial velocity has been given to us as 0, and therefore we will be able to be good to go. So if in other cases you are told that this is supposed to be equal to g of x, another function of x, then therefore this function of x is equal to 0. So next point is we need now to assume solutions. So assuming the solution of the PDE, the solution of the partial differential equation. So we are told that u being a function of x and t, okay, we can assume a solution equivalent to x of x times t of t. And when we simplify this, so simplifying this gives u equivalent to xt. So now once we have that simplified form of the solution of the partial differential equation, we are going to take partial derivatives. So let's take the partial derivatives. We will have del 2u del x2 is going to be x double prime, then t. We differentiate x, we are going to differentiate this u with respect to x, keeping t a constant. Then del 2u del t squared is going to be x t double prime. We are also going to differentiate u with respect to t, keeping x a constant. And that is what we are doing here. So meaning if we substitute in the partial differential equation, so substitute in the PD above. So meaning wherever we have del 2u del x squared, we shall put x double prime t. So x double prime t will equal to 1 out of c squared times x t double prime. But remember, but c squared is equal to 1. So meaning we are taking x double prime t equivalent to x t double prime. So separating the variables, what would this give us? Separating variables, we would have something like this. X double prime out of x equivalent to t double prime divided by t. So finally, this is, maybe let's call this equation, we can call this other first one. This one here was our equation 1. Okay. So let's go and make this. We make this f of x for the two ranges b. We are making this as equation. We are making it equation number 2. Then we are making this equation number 3. So we are going to select x2 out of x is equal to t double prime out of t equal to negative p squared. So whereby negative p squared is a constant. Why? Because if x is a function of x only and t is a function of t only, is a function of t only, is a function of t only. So meaning if this is a function of x only and this is a function of t only, then if I do this, I differentiate this with respect to x, I differentiate this with respect to t, what if the two are equal, then they are going to equal to a constant. So for convenience, we are taking negative p squared. Why we are taking negative p squared? If you have been attending some of our discussions, you'll understand. Because this is the only case that gives us the desirable solution that is oscillatory. Otherwise, if it was only p squared or equal to 0, we would get non-oscillatory solutions. So let's go ahead and generate ordinary differential equations out of this. So this becomes plus x p squared is equal to 0, and we'll have t double prime plus p squared t is equal to 0. So let's call this equation 4. So now from 4, solving 4, we get, remember you apply auxiliary equation. So after getting the auxiliary equation, then you are able to get the solution to this ordinary differential equations. So you will have the auxiliary equation being m squared plus what? Plus p squared is equal to 0. So m is going to be plus o minus jp. And therefore, this gives us equations that have sine and cos. So this is going to be x is going to be a cos px plus b sine px. Then t itself is going to be what? It's going to be also, maybe we can say c cos pt, okay? pt plus d sine pt. So, meaning that therefore u equivalent to xt will therefore become a cos px plus b sine px, and then we multiply it by c cos pt plus d sine pt. Okay, so from here we have those big equations, and what we can do with them is now applying boundary conditions. So let's apply boundary conditions. Start applying boundary conditions. So when you apply boundary conditions, the first one was at x is equal to 0. So u0t, we said is equal to 0, so we're substituting our t, I mean x is equal to 0. So this becomes what? This becomes a then plus 0, okay? Because the sign of 0 becomes 0 and the cos of 0 becomes 1. So times a, you'll have a plus 0. Then we are multiplying it by c, then cos pt plus d sine pt. Okay, so that's what we have, and this is equal to 0. So we'll have a times c cos pt plus d sine pt is equal to 0. So what we are going to do, we are going to multiply this throughout. Okay, let's first see. If we have a is equal to 0, okay, then what happens? Because we know for all values of t, for all values of t, we will find that this cos c cos pt plus d sine pt, it will never be 0. So if this can't be equal to 0, okay, then a can be equal to 0. So this gives us what? It gives us a solution where a is equal to 0. We are going to come up with u x e, therefore reduces to be sine px, and then we'll have c, okay? We'll have c cos pt plus d sine pt. And then if we can look at this, we can once again go ahead and let's apply a second boundary condition. The second boundary condition whereby u of L t is equal to what? Is equal to 0 also. So we are talking about u of 50 t is equal to 0. So we are going to put 50 wherever x is, so that we have 0 is going to be p sine 50, then p, then we multiply it by c cos pt plus d sine pt. So if this is to hold for all values of t, then this is never going to be equal to 0, never equal to 0. This can never equal to 0, but then it leaves us with a choice of now only this component to be the one to equal to 0. So sine 50p can equal to 0. So if this is going to be possible, then we shall have that 50p is going to be equal to n pi, whereby n is equal to 1, 2, 3, and so on, those integers. Because when you take sine of 180, you'll have a 0, sine of 360, you'll have a 0, 584, you'll have a 0, so you continue and continue and continue. So p, therefore, will be n pi out of 50. So that's what we are doing. And then, therefore, we will have u x of t is equal to what? It's going to be b sine n pi x out of 50. Then we are going to maintain our c here, then cos. What is this now? This is going to be n pi t out of 50, then plus d sine n pi out of 50 t. So remember, we can multiply now this BC throughout here so that we have something like this. So BC, let this equivalent to P, and then 2, let it be BD. So, and if we consider considering many values of u x t, since we are talking about n equivalent to 1, 2, 3, we are going to be having many values of u x t. So this is going to happen. We shall have u x t equivalent to what? This is going to be equivalent to P. Okay, let's take a sum from n is equal to 1 up to infinity of P, P cos. So we have cos n pi t out of 50 plus 2 sine n pi t out of 50. Then everything we are multiplying it by sine n pi x out of 50. So now, if we just simplify this, remember we know according to Fourier series, we can just simplify this. So what we are going to do, we are going to say un, since we're talking about many values of uxt, will equal to the sum from n is equal to 1 up to infinity of n. So we introduce in the coefficients of Fourier series. So the Fourier series coefficients, we are going to write an cos n pi t out of 50 plus bn sine n pi t out of 50. Then we are multiplying by sine n pi x out of 50. So once we are here, we are going to be looking for the Fourier coefficients. So Fourier coefficients an and bn. So we earlier on had introduced on how we can find these an and bn for a one-dimensional wave equation. I'm just going to quote again those equations, and this is going to be like this. We are going to have an itself is going to be 2 out of f times the mean value of f of x, okay, sine pi x out of L. So from 0 to L, f of x sine n pi x out of L with respect to x. But remember, f of x, we have f of x equivalent to, we say the 2 out of 25x for 0 less x less 25. And we also had, negative 2x out of 25 plus 4 for 25, okay, less x less 50. So this is in a piecewise form. So this is what we are going to apply in order to get an. So we shall therefore have an, which is equal to integrating actually 2 out of L, which is this is 50. So integrating from 0 to 25, first of all, let me create a bigger bracket here. So from 0 to 25 of 2 out of 25, this is x. Then sine n pi x out of 50 with respect to x. Then we add integrating from 25 to 50 of what? We had 100 minus 2x out of 25. So remember, we have a sine pi x out of 50 with respect to x, and we cross. So this involves integration by parts. So this is integration by parts. So concentrate on this by integration by parts, and then make sure that you get this expression. I'll not spend a lot of time on this since I'm sure you are aware of how to do this. So just make u equal to x, then the x equal to sine n pi x divided by 50. In other words, we are saying that integrating u dv dx with respect to x is equal to uv minus integrating of integrating v du dx with respect to x. So make x equal to u, differentiate it, make sine n pi x out of 50 equivalent to dv dx, then integrate it. so that you now substitute it in here and continue. So my an, when I did the integration, this is what I got. I got 16 divided by n squared sine n pi out of 2. So what about Bn? I'll be talking about Bn as now a coefficient of sine. So this is a coefficient for an odd function, a sine. So this is also given by, I remember I also talked about it, and this is what we had in our past lectures. Cn pi integrating from 0 to L of g of x sine n pi of x divided by L. But we know C and we know g of x. We know g of x is actually equivalent to del u del t, okay, at t is equal to 0. And this is equal to 0. So if it becomes 0, if we put 0 here, everything becomes 0. Hence, Bn is equal to 0. So what we are going to do is to substitute these coefficients. So substituting the coefficients in the general equation gives, so this is what it gives. I will have u xt, this is going to be equivalent to, remember I have a sum from n is equal to 1 up to infinity of sine n pi x out of 50. Yes, error is equal to 50. Then we create a bigger brackets. Remember we had the an, then an sine. This was actually cos n pi t out of 50, then plus bn sine n pi t out of 50. But remember, we have said this bn is equal to 0, and this n is equal to 16 out of n squared, pi squared, sine n pi out of 2. Therefore, the equation of motion of this wave within a string given to us is going to be summation from n is equal to 1 up to infinity of sine n pi x out of 50. Then we are going to multiply by 16 divided by n squared pi squared sine n pi out of 2, and then we are multiplying it by cos n pi t out of 50. So this gives us the equation that brings us to the end. This is the solution. This is the solution of the given problem. So it represents the equation of motion of any particle. Okay, let me say of any particle or displacement of any particle on the string when set to oscillate. So this is how our solution looks like, and thank you for tuning in, and remember to always follow us, turn on your bell button, and make sure that our notifications are always linked to your device and you are always ready to find any new of our updates. Thank you so much.